go. So we'll put length on our x-axis and energy, potential energy on our y-axis. Our potential is centered at L naught, the rest length of the spring, and the energy increases quadratically as a function of displacement. Okay. So I want to talk a little bit about how do we relate this potential energy to the solution. All right, we know that the length of the spring is moving oscillatory, so what does it look like in terms of energy? And I have maybe a better way to draw this. You bear with me. Let's go ahead and redraw my big coordinate, my potential energy surface here in the middle. And I probably should have just done this at the beginning, but bear with me. L and V of L. All right, and we'll mark this L naught. Here's our minimum. Here's our potential. 1/2 kx squared, or kl squared. Sorry, let me make that precise. All right, so let's think we have a spring, okay, that has some stiffness and some length, all of that jazz. All right, and let's take that spring and let's extend it, okay, to some fixed point. All right, so let's say, for instance, we stretch it to here. All right, so we'll call this L of 0, right, for t equals 0. All right, so we've stretched the spring out, right, because we've had a positive displacement relative to L0. The spring is now longer than it is at rest, so we've stretched it. And then what I want to do is I want to let the spring go. And I want to see how the spring oscillates, right, on this potential. How does the energy of the harmonic oscillator change as a function of time? Well, if we think about this, the force that's acting on the spring at this point is in this direction, right? The force is in this direction, right? Remember, it's minus KL. L is positive here, positive displacement, so the force is negative. It wants to retract the spring. So what I want to do today, or what I want to do here, is I want to plot the displacement of my spring as a function of time on a different graph. So what I'm going to do is this. I'm going to put a horizontal line somewhere in the middle here, which will represent L naught. Okay, and let me just make this a little taller. I just need a little bit more space. All right, good enough. Okay, so let's say we now, and let's let time go to the left. All right, it just makes our math life a little easier if we let time to increase from the right to the left instead. Okay, you'll understand why in a second. So at t equals 0, where is our spring's position? Well, our spring's position is at L of 0, and that's at a positive number. So we'll put it here. That's our first point on our spring. Okay, and now what we're going to do is we're going to let it evolve in time. We're going to let go of our spring and allow it to move. All right, and the force is acting on it to compress. So the spring will start to decrease in length. Let me make it go a little slower than that. Start to decrease in length, right? That's it going down this potential. And eventually it'll cross L0, right? That's when it hits the bottom of the well. Okay, and at this point, so here the energy of L is maximum, and the kinetic energy at this point is 0, right? Because it's all potential. At the beginning point, the spring's not moving, so it's all potential energy. So here at the bottom, the spring now has no potential energy, but energy is conserved, right? So V here is equal to 0, and that means that T is maximum. All right, so at the middle point, right, when the spring comes back to its original point, now it has maximum kinetic energy. It wants to keep moving, right? And it's just going to keep moving in the same direction, right? That's Newton's first law. So the spring is now going to contract past this point. Right? So it's going to go down. It's going to decrease, decrease, decrease. And eventually it's going to hit this point right here on the opposite side of the potential. We'll call that V of 0. Right? Because the system is energy conserved. Right? You can only have as much energy as you put in. So I put in this much energy, and so the system will never have more energy than that. Okay, so this is the furthest extent on the opposite side, the compressed side, that it's going to go. It's going to go from here to here. And it's equal, it's on the opposite side of the center, right? So I could say that where the displacement goes to minimum is at negative L of 0, right? It's just oscillating to the other side. And then the system does the same thing again. Right? It just keeps going back and forth, back and forth, back and forth. Right? So when the spring gets up to this point of minimum displacement, well, now the force is acting in the opposite direction, and it wants to now extend. Right? So what's basically happening, you can think of it as a ball that you have this big hill that it's rolling on. You drop the ball here, it rolls down, rolls back up to the other side. It can't go any higher than that because it doesn't have enough energy. And then it rolls back again, it rolls back again, it rolls back again. Right? So that's where that sine comes. Well, this is a cosine, of course. Right? So this is some cosine function. And it's a cosine because we started the physics at the furthest extent. Right? So this is this function here. So we'll say that L of t, I'll write it over here, is equal to L of 0 times cosine omega t, where omega is something to do with the stiffness in the mass. Okay, and of course the frequency is the measure from this point to this point, right? This is 2 pi omega. This time difference, right? That's 2 pi omega. Right, so the rate at which the spring extracts and extends, extracts, extends, the rate at which it does that, the speed, right? How long it takes to. Sorry, I think my coat did that. Yes, I did. Thank you. So the time it takes to go from one extent to the other is dependent on the frequency, which is the stiffness of the spring. So if you have a really lazy slinky and you do this, it goes very slowly. Right? If you have a really big mass on it, it goes really slowly. But if you have a really, really tight spring, like one in your car's engine, you know, really, really tight, very strong spring, this frequency is very fast, and the spring oscillates very quickly. Okay? So it's very interesting that you get this oscillatory behavior from something that doesn't look oscillatory, but this is the idea, is that because energy is conserved at this point, the system just oscillates back and forth between these 2 points on the edges. And these points, I mentioned that last class, but I'll redefine them for you. These points right here are called the turning points. All right, the turning points. All right, these are the points at which the spring now turns around. Right? That's why they're called turning points. Right? It stops here and then goes backwards, and stops here and goes the other way. Right? And the point of the matter is that in the classical spring, right, if the energy of my spring is right here at V equals 0, that's how much energy my spring has always, and it can never have more than that. Right? So this point and this point are the farthest extents of the spring given the energy you put into the system. All right? It can't be any longer than that. All right? So these are fixed for a classical spring, fixed by the amount of energy. Put into spring. And they're the maximum extents of the spring. Maximum displacements. Right? The spring can't displace any further than this. All right? I want to emphasize that point. That the maximum extent of our oscillator entirely depends on how hard we stretch it initially. Okay? And it can't go any further than that displacement, either negative or positive. Right? These turning points are fixed. Right? I mention this, and it might seem obvious to you that this is the case, because if you think about a pendulum, for instance, if you have, maybe you've seen these videos, if you do them at MIT, there's a famous physicist at MIT who's got these videos on YouTube named Walt Levin. He's not so famous anymore because he had been banging his students for 40 years, so he's not the best person in the world, but he has great physics videos on. And he has a classic experiment where he puts a student in a chair, sits here, and has a long string of a bowling ball attached to it, and he puts the bowling ball right up to their face like this, right in front of their nose, and lets it go, lets it swing, and of course it never hits their face again. Right? In fact, because it loses energy, it never gets as close as it did from the beginning, but it never swings back and hits them in the face because it doesn't have enough energy to do that. Because its turning points are right there at your nose, right there, right in front of you. So if it's initially 1 inch away from your nose, it'll never get any closer than that without putting more energy into it. So these turning points are hard. They're hard fixes, right? They're hard fixed points. Again, it seems obvious, but we're going to see in quantum mechanics, when we talk about the quantum mechanic version of this gets broken. A quantum mechanical oscillator can has probability to exist beyond the turning points at a given energy, as we'll see. So we could say that, for instance, if we have we put some energy into our bond, maybe it's at this energy. Classically, we would say it never be smaller than this or bigger than this when it vibrates. But in fact, in a quantum mechanical oscillator, it can be smaller and it can be bigger. In fact, it goes to infinity. There's a probability that your bond is a light year apart. Your bond's a light year long. You can calculate that probability. Of course, it's vanishingly small, but there's a probability of that the bond is delocalized across all space. Right? That's very different than a classical spring, obviously. Right? So we'll see that. It'll come up very, very quickly when we start looking at wave functions and energies for our system. That these turning points are only classical. That in fact, a system can exist beyond them, even at a given energy. And we'll see that. Okay. So this is kind of all I want to say about a classical oscillator. Let's go back now and talk about the quantum mechanical one. All right. So now that we have a sense of how this works, I posted on Canvas a little harmonic oscillator simulator. I think I posted it for you guys on the Canvas announcements. You can play around with this if you'd like. So let's look at let's apply now quantum mechanics to this. Right, when I write HO, that means harmonic oscillator, and generally I'll call this the QHO, the QHO. So we have the pain in the butt and the QHO so far. So what we want to do in every problem that we set up in this class, or in quantum mechanics, the first thing we want to do is we want to solve the Schrodinger equation. H psi is equal to E psi. Right? This is what we do every time. So we have to come up with a Hamiltonian and then solve for the set of equations that or the set of formulas or the set of wave functions that satisfy this formula. And I introduced the Hamiltonian, I think last class, but let's go back through it again. Hamiltonian is a sum of the kinetic and the potential energies. Ken and pot. And we know what the kinetic energy is. It's the same as the harmonic. The kinetic energy term is basically the same in every problem. It always looks like p squared over 2m or minus h bar squared over 2 times the mass of the system, which is mu, times the second derivative with respect to position. Here I'm using x as our bond length. Okay, we'll talk a little bit about that in a second. And then we have a potential energy, which is a function of the bond length. But we know what this potential is. We calculated it for the harmonic oscillator. Right? So what we're going to do now is we're going to apply our classical potential. Okay? And so we know that it's 1/2 kx squared. So our Hamiltonian now is minus h bar squared over 2 mu times the second derivative with respect to x squared plus 1/2 kx squared. Okay, that's our harmonic oscillator potential. Right? If I rearrange this equation a little bit, right? So now what I'm going to do is apply Schrodinger's equation. And what do I have? I'm just going to do a little bit of a rearrangement here. I get the second derivative of the wave function with respect to the displacement is equal to minus 2 mu over h bar squared times the energy of the system minus 1/2 kx squared psi. So what I've done is I've applied psi to our operators and I've rearranged the terms a little bit so I get this nice equality. So let's look at what we have here. So let me remind you what the particle in the box equation looked like. So this is our QHO problem. This is our QHO Schrodinger equation. For the particle in the box, what does our equation look like? Well, again, on one side we have d squared psi dx squared, second derivative, is equal to minus 2m over h bar squared e times psi. Okay. So what do we have for the particle in the box? Remember, what does it say? It says that when we take the second derivative of our solutions, we get the same function back times some numbers. Okay. All right. So we saw that the solutions to that are sines and cosines. But now we have additional problem for the harmonic oscillator. Now we have an additional complication. Is that when we take the second derivative of our wave function, we get some constant factor back, but we also get the wave function with x squared times back. We get the argument outside. So you can kind of think of this as being functions where when you take the second derivative of them, you get x squared times psi. Right? Instead of a constant, now your thing that gets factored out is a variable. Right? So sine and cosine won't work in here, right? Because you take the integral, if sine were sine, the first derivative, right, the second derivative of sine is minus sine x. Right? There's no x that comes out of that. Right? So maybe we could do something very simple. What if, for instance, we guessed, I'm just going to put this in a box on the side. What if we guess psi is equal to sine of x squared? Maybe that's a good option, right? Because what happens when we take the derivative of this? D psi dx is 2x cosine x squared. And the second derivative, well, as you can see, the second derivative gets complicated because we have a product rule now. We have 2 cosine x squared minus 4x cosine x squared. Oh, sorry, x squared. Sorry, there's an x squared there. Right? So when we take the second derivative of sine of x squared, we get this x squared cosine. I forgot to take a sign. Sorry, there's a sign here. Right? When we take our function and we take the second derivative, we get the x squared times our function back. But notice that we get this cosine x squared. Right? That's not in here. Right? We should get sine, a constant times sine of x squared minus x squared sine x squared. Right? So this number right here, this number right here, this 2 cosine x squared, that should just be a number for this to be a solution. So this doesn't work. We can't use sines and cosines for this problem. Right? This works, but this doesn't. Right? So this goes away. Right? This doesn't work. Okay, so we have to come up with a new function. Right? And there's another reason why this doesn't work, as we'll see. All right? So we can't use trigonometric functions to solve this equation. Thankfully, I have two good pieces of good news for you. First of all is that there is a solution. There is a set of functions that satisfy this, and we can write them down, and we will. And second of all, we're not going to worry about how you derive them. This is the first point in this class where we're going to have this differential equation, right? We have the derivative, second derivative of something equals the function times an argument of its variables. That's a pretty hard solution to solve. If you've taken differential equations, which probably none of you have, you'll see solutions of these things. But I don't want to go through the math of how to solve this equation because it's just not worth it. All right? What's better is to think about what the solutions are because they're well known, they're well studied. We can write them down, easy formulas for them. And the physical interpretation of them is very, very interesting. So all of the things that we get to do with those functions is what I really care about. So this is the first time where I'm going to say, I'm going to solve this equation and we're not going to worry about the derivation. Okay? So I want to talk about what the solutions of this look like. Right? And it turns out that this is a very, very common differential equation, this idea of taking the second derivative of a function and getting something that's x squared times that function. It's a well-known set of problems, and they were solved in the 1800s. So there's actually the solution to heat transfer, for instance. When you talk about the equations of how heat flows through materials, and how a wave propagates through materials, you get equations that look very similar to this. Okay, so when people studied heat in the 19th century, they came up with equations that look like this for their physics, and so they figured out how to solve these things. So we can just use all of their good work. All right. So let's talk about what the wave functions for the harmonic oscillator look like. Okay, so we're going to solve. So we're going to let better mathematicians. You don't have to write this. I was just going to joke. Let better mathematicians solve the problem for us. And if you have the textbook actually does go through the solution set for this derivation, and there's plenty of resources online if you're interested in how this is solved. In fact, Wikipedia has a very nice discussion of it. All right, and our solutions, I'm going to write them down, and there's going to be a bunch of different kind of variables and stuff and constants, and I'm going to define everything slowly, so bear with me. You're going to see a bunch of things that you don't recognize, but we'll work through them. So the solutions to this are indexed by this letter v, and again, they're functions of x. All right, this v here is like in a particle in a box n. It's our quantum number, right? It's a number. It's an integer. This is called the vibrational quantum number. V, all right? And V, let me write this in a different color so it's obvious. V can run between 0 and infinity. So V takes any value from 0 and up. I'll just kind of mark that like this. Okay. So this is already different than a particle in a box. Remember, particle in a box, the lowest value of n is 1. Because if n is 0, the only wave function that satisfies that is a 0 wave function, null wave function, which means you have no particle. So the only valid n equals 0 state of a box is an empty one. But here, you get a solution where v can be 0. There is a 0 ground state for vibrations. Right? We'll talk about the repercussions of this. Right? But it's just good to note that instead of running from 1 to infinity, it runs from 0 to infinity. Okay? And the wave functions look like this. I'm gonna draw each component in a different color, so I can tell you what they each mean. So the first part of it is the normalization constant. It's the thing that makes the function integrate to 1. It's 1 over the square root of 2 to the v factorial, and I'll remind you what that is in a second, times another number alpha, I'll write what alpha is in a second, over pi to the 1/4 power. Okay. And then, so this is the normalization constant. Right, this is normalization. It's just a number. And I'll define everything in a second. Let me just finish it. And then what we do is we multiply this function, this number, by a special kind of function, a named function, a special function called a Hermite polynomial, which is I note as h sub v. And it takes in, as its variable, the square root of this alpha number times x. Right? This just makes it unitless. Right? I'll show you what this looks like in a second. And then we finally multiply the whole function. All right, let me write this. This is what's called a Hermite polynomial. All right, and I will write down the polynomials for you. What these functions look like in a second. And this is all multiplied by one more term. I don't have enough space. There's this e to the minus alpha x squared over 2. All right, and this function has a very special name. As two names that we often call it. A mathematician or a physicist or a chemist, we all often call this a Gaussian function. But you guys know and love this function as a bell curve. This is a classic bell curve or a normal distribution. All right, when you think bell curve, the function for a bell curve is e to the minus x squared over 2. Okay, so let's talk about this a little bit. So our wave function has a number that normalizes the function. There's this special function that we don't know what they look like yet called a Hermite polynomial. This is a function h that takes in, this is not h times this, function h that takes in the argument alpha 1/2 x. All right, so we're going to plug in this number alpha, square root of it times x into this function. Okay. So not a multiplication, this is a function. I'll just write that at top. hv of x is a function. All right, it's a special function. They're tabulated, so we can write them down. All right. Each v, notice that in this problem, that each Hermite polynomial has an index v. So there's one for v equals 0, there's one for v equals 1, one for v equals 2, and so on. They're not that hard. They're not that complicated to understand, but there's going to be a different one for each state. And then the most interesting part of the function is this. The e to the minus alpha x squared over 2. Right? There's no sines or cosines in here. Right? So this part right here is this equivalent form of the sine plus cosine for the particle in a box, but now it has this function we don't know what it looks like yet, times a bell curve. Right? We might want to plot these and look at them a little bit. But before I do that, let's define a few things. Okay, so let's just get everyone on the same page here about the math, because again, there's a couple of complicated things here. So let's just define a few things. Alpha is a constant, and it's the square root of the stiffness of the spring K times the reduced mass divided by h bar squared. Okay, so alpha has something to do with the spring material, the spring parameters. Okay, pretty easy. Again, let's remind ourselves, if you don't remember, a factorial is a product of all numbers up to that point. So the factorial of n is the product of n times n minus 1 times n minus 2 all the way to 2 times 1. So just as an example, I'll just do a quick example for you. 4 factorial is 4 times 3 times 2 times 1, which is 24. And there's one more definition I want to do, is that 0 factorial is 1, right, by definition. Okay, so 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1. That's 6. 4 factorial is 4 times 3 times 2 times 1, which is 24, and so on. Okay, easy to calculate. And those are all of our numbers. And so now we have to talk about these Hermite polynomials. And I'm just going to write down a couple for you. There is a formula. There is a list of them. I think there might be a list of them on Canvas. There certainly is in a book. And you probably won't need any more than the ones that I give you here anyway. So what I'm going to do, I'll put them down here. Let me give it a little more space. So let me mark some things off, just to kind of consolidate my space here. Definition. Okay. And so let's look at the Hermite polynomials. And then we'll put everything together after we're done. All right, I'm going to let z equal alpha. I'm just going to make things easier. I'm going to let z equal alpha 1/2 x. So our variable is z. And H0 of z, right? So that's the Hermite polynomial for v equals 0. It's just 1. It's just the number 1. Okay, easy enough. The Hermite polynomial for v equals 1 is 2z. Hermite polynomial for v equals 2 is 4z squared minus 2. And a Hermite polynomial for v equals 3 is 8z3 minus 12z. Okay? So let me put this together. All right, now that I have everything written down for everything, I know it's a lot of stuff, but we'll see how it simplifies very quickly. The Hermite there's a reason why it's called a polynomial, because the Hermite polynomial is a polynomial. Okay, so it's just a function of the coordinate, right? And the v, right, 0, 1, 2, 3, right, the quantum number determines the order of the polynomial, right? So for the ground state, the Hermite polynomial is just 1, right? That's a 0th order polynomial. There's no powers of z. H1 is a linear function of z, right? It's z to the 1. Maybe it's worth writing that here, right? Z to the 1. Right? It's a linear function, first order function of the coordinate. V equals 2 is a quadratic function. V equals 3 is a cubic function. And you can imagine that the Hermite polynomial for v equals 4 is a quartic function, and then a quintic function, then a sextic function, right? So the v tells you what order the polynomial is on the outside, and there's special ones for each v. Right? There's a formula you can use to calculate them, which we won't need in this class because we'll never really think about things more than d equals 3 in this class, for good reasons, as we'll see. So these are the ones we need, but the point is that our wave function looks like, for a given v, a polynomial of order v times a bell curve. Right? That's kind of a funny looking function. Right? Doesn't really look like a sine or a cosine. Remember, we have waves. We're treating things like waves. And the question is, are these look like waves? A bell curve times a polynomial. That doesn't look like a sine wave. Right? So maybe we should plot them and look at them a little bit. All right, so I'll come back to these in a second. So let's go ahead and plot them. So the way I'm going to plot these, I'm going to draw my coordinate system. All right, I'm going to plot energy on this axis and displacement on this axis. We'll say that the rest length of the bond is at XO. All right, that would be the rest length, LO. I'm just using X's here instead of L's. but it's the same idea. And there's and the potential energy is a parabola centered around XO. I'm going to make this a little wider if that's okay. I'll make it a little broader just to kind of give myself some more space. All right, so this function again is v of x is equal to 1/2 k x minus x naught squared. Okay, and now what I want to do is I want to draw my energy levels and my wave functions for each of the v's. But here's a problem. I'm just going to go back a page. You don't have to write anything in. I haven't talked about the energies yet, just just the wave functions. All right, so we have these complicated wave functions we need to look at, but what are the energies of each of these states? All right, so before we do that, let's think about that for a second. What's the energy of the system? What are the eigenvalues? All right, and I'm not going to derive this, but if we have some time later, and maybe the week before spring break, I will show you a very, very beautiful derivation of this formula. Very, very elegant formula. Derivation. The energy of a quantum harmonic oscillator, again, is a function of the quantum number v. H bar omega v plus 1/2, where omega, just like it was for the harmonic oscillator, the classical one, is k over mu. All right, remember that v can be 0, 1, 2, and so on. Very, very simple formula. Right? We have a frequency. Right? This has units of energy. This is a frequency. This is Planck's constant. H times Planck's constant gives you an energy. So this is energy times a number v plus 1/2. Right? And the energies are determined, the spacings of the energies are determined by the stiffness of the spring. If you have a really, really stiff spring, your omega is very high, which means you need to put a lot of energy into it to excite it. But if you have a very floppy spring, very slow, floppy, kind of slinky spring, you don't have to put a lot of energy into it as v goes up. Right? Omega is small. Right? Here's the most important factor. Right? So the question, of course, is where is the ground state energy? Where's v equals 0? Well, v equals 0 would be where v is 0. So that's 0 plus 1/2 times h bar omega. So the ground state energy of our harmonic oscillator is not 0. It's at 1/2 h bar omega. Remember, just like the particle in the box, when we put an electron in the box, it has to have some energy. Energy equals 0. The only state that has energy equals 0 in a particle in a box is a null wave function, which is no particle at all. An empty box is 0 energy. And that's the same thing for our harmonic oscillator. A bond always has energy. Right? So you can imagine, going back to thermodynamics, talking about the laws of thermodynamics, the third law of thermodynamics says that it's effectively impossible to reach 0 Kelvin. What is 0 Kelvin? A system at 0 Kelvin is a system without any energy in it. Okay, so imagine you have a gas of these molecules, and you want to cool it down to absolute 0, right? So you remove all the energy, you cool it down, cool it down, cool it down, and everything's in a ground state, right? All your molecules are in their vibrational ground state. They're all in v equals 0, and each one contributes exactly 1/2 h bar omega of energy. So no matter how cold you make the system, there's always, if you have n molecules, n times this number worth of energy. So no matter how hard you try, the system will always have energy and can never be at 0 Kelvin. There's always some residual energy, just like in a particle in a box. Right? The term we call this 0-point energy. Right? And every bond has this little energy. What's the consequence of this? The consequence is that even if your bond, all your molecules are in the ground state, right? No energy in them. They're as cold as they possibly can be. Those bonds are still oscillating a little bit. right? They still have some energy, which means they have a little bit of momentum, right? Therefore, they're still oscillating. Bonds always vibrate. They always have some small amount of residual energy in their vibrational modes. So they're always vibrating. You can't get rid of it, right? And that's that 0 point energy here. This is the minimum amount of energy you can have in a bond. You can't have any less. That's clearly different than the classical oscillator, right? Because what happened with the classical oscillator, the system like if we stretch it to this energy, it goes down in potential and then back up again, right? The potential energy changes as a function of time as the system moves back and forth. That does not happen here in quantum mechanics. You fix the energy here, the energy can't be any lower, the potential energy can't be any lower than that. So the potential energy is fixed for the quantum oscillator, and it's always here. It never goes to zero potential. It always vibrates with a little bit of energy. This has deep, deep consequences. I'm not quite ready to tackle those consequences yet, but we will next class. And I'll return to this point next class. So what does the wave function look like for this? This is the v equals 0 state, of course. What does the wave function look like for this? I'll just put them on the side here. Psi of 0. We're going to ignore the normalization constant. Let's just ignore that normalization. Just look at the Hermite polynomial and the function, the bell curve. The Hermite polynomial for v equals 0 is 1, just the number 1, times e to the minus alpha x squared over 2. Okay, so the wave function for the harmonic ground state just looks like this exponent, right? It just looks like a bell curve. It is a bell curve. It literally is. It's a normal distribution. It's a bell curve. So the wave function for this, I'm going to erase, yeah, that's fine. We'll just do it like this. Looks like a bell curve like that. And of course, the bell curve is centered at the middle of the bond. It has some width. But the important point about this function, right? Take x to be, where does this wave function go to 0? Now remember in the particle in the box, where does the wave function go to 0 in the particle in the box? At the walls, right? Psi is 0 at the walls. Right? What's the equivalent of the walls here? Well, it's the potential. Right? These are the turning points, if you will. Right? These two right here. These are the kind of the edges of our wall given the energy, if you think of it equivalently, like that. But if you look at this function, and you put a finite number here, right? You put the turning points right here into this value of the wave function, it's not 0. It might be small, but the only values of x where this function disappears, it goes to 0, is at infinity. Right? So this function decays outside of the box. It doesn't go to 0 at the edges, at the turning points. It goes to 0 at infinity. So, in fact, outside of the box, if we were to integrate, and we will do this next class, there's a little bit of amplitude outside of the potential. Because the function goes out to infinity. It goes to 0. It's asymptotic to 0. What does that mean? Well, when we calculate the probability of finding the wave function, the system, outside of its turning points, which is that the wave function, we find the system here or find it here, we'll do that calculation. It ends up being about 16% of the time. So only about 84% of the time the wave function exists between the turning points. And the bond can be longer, it can be shorter than that too, about 16% of the time. We'll do that calculation exactly. But that's because this is a bell curve. Right? It's a normal distribution. You can have you have non-zero probability of any finite value in a bell curve. Of course, it's vanishingly small, right? This is a very small integral compared to the middle part. So on average, the bond is within the turning points. But we'll see that as there is some probability of it being outside of them as well. There's our magical bell curve. So let's look now at the next level. V equals 1. All right, what's the energy of this state? Well, now we just plug in 1 here. Now we have 3 halves h bar omega. Okay. And our wave function for this system, go back and look, the Hermite polynomial is just a linear function, so it looks like x times e to the minus alpha x squared over 2. All right. Now, what I'm just going to, just really careful here, and I've been a little sloppy, is that my potential is centered at x naught. But the way that I've written these are centered at x equals 0. Okay, so I've shifted everything to x naught. So really this should be x minus x naught e to the minus alpha x minus x naught squared. I've shifted everything. So I'm just being a little sloppy here. But in this formalism, the center, this point right here is x equals 0. Okay. We won't worry about that too much. So, but anyway, so you can think of x naught as kind of being the origin of our potential. And so let's think about what this function does as a function of x. So again, this function is symmetric about x. If I take a value less than x naught or a value greater than x naught or a positive x or negative x, however you want to think about it, I get the same thing, right? E to the minus x is psi of minus x is the same as psi of x, right? It's an even function. Right? It's an even. Oh, let me write that clearly, sorry. Right? What about this function? Well, this is even, right? It's the same thing, but now we have this x, right? So when x is negative, or x is less than x naught in this case, you get a negative sign on the outside. Right? So that means that the negative x's are inverted from the positive x's. Right? So you get a change of sign about x equals 0. So this is an odd function. So it changes sign about the center. And it's going to be negative on the left side, positive on the right side. So the wave function for this will look something like this. Like that. Okay. Again, you might already see the pattern. I'll do the next one, just as an example. But maybe there are oscillations in this function. Maybe these do look kind of like waves, right? Because you think about the particle in a box. Remember what the particle in a box wave function looks like. N equals 1, it looks like a half period of a wave, a sine wave. This kind of looks like a half period of a sine wave. N equals 2 is a whole period. Well, this looks like a whole period of a wave. It's got one node. Right? It's got everything that we wanted. But the functional form is not really a sine wave or a cosine, but it kind of has the behavior that we want. Right? It oscillates in some respects. And it's also symmetric about the center, like we expect. So that's a good sign. So let's just do one more, just to kind of drive the point home. I'm going to extend my potential up a little more, just to have a bit more space. So let's do V3. V equals 2, sorry. What's the energy of this? Well, now V is 2. 2 plus 1 half is 5 halves. H bar omega. And psi 2, again, remember it looks like a quadratic function times a bell curve. And this function is even, right? Because if I take negative x, square it, L becomes positive. Right? So this is even again. Right? So if I were to plot it, it's not too hard to plot. It goes up like this, comes down, comes up again, and then goes to infinity. Actually, so it doesn't go to 0. So that's the important thing. It doesn't go to 0 at the turning point, so it actually kind of decays out. Like this. Okay, again, does this look a lot like the functions that we saw for the particle in a box? Of course, they have very different form, but graphically they look exactly the same. Right? Within the box, within the potential, within the turning points, these systems are sinusoidal. They're oscillatory, and they're oscillatory in exactly the same way we want them to be. Right? This looks like a half period, a whole period, a period and a half, right? It's the same behavior as the particle in a box in terms of the way the functions oscillate and move. But the big difference between this is that these functions don't go to 0 at the turning points. They extend beyond the turning points. Right? Because this part right here right, asymptotically approaches 0 at infinity, not at the turning point. Okay? So again, the physics are very similar. We still have wave-like behavior inside of the potential, but now we have this magic kind of decay behavior on the outside of the potential past the turning points. Right? The idea is that if we look at the potential kind of like this, so here's my potential, and I'm just going to pick a level, is that inside the potential, inside looks kind of like sine or cosine of n omega t. And then on the outside of the function, outside of the wall, it decays away. And let me make sure that this is symmetric. Sorry, guys. It's kind of sloppy. It's got to be symmetric. There we go. Something like that. It's got to be the same on both sides. Right? And then on the other side of the function, outside of the potential, it goes to 0. Right? And this looks like e to the minus x squared. Okay, so inside of the box, between the turning points, the system oscillates exactly the way you expect it. It goes back and forth, back and forth, back and forth. It has that wave-like behavior that we expect. Right? All the particle in the box things that we were thinking about kind of work here, kind of qualitatively. But the important point is that this box is leaky. Right? Because in order to be, say, right here, right? Right? It takes a finite amount of energy to get to that point. Right? And the particle in the box, of course, it takes infinite energy to cross the turning points. Right? Because the boxes are infinite. But the potential is not infinite at this displacement. Right? If I draw a vertical line up from this point in energy, eventually I'm going to intersect some finite value of the potential. So that means that there's a finite energy cost to escape the box in this case. And the probability of escaping the box is exponentially decaying. It decays very quickly. It decays as e to the minus x squared. Very quick exponential decay. But it decays. Right? There's a non-zero probability of being on the outside. Right? This is a leaky box. Okay? It's leaky. So inside of the box, it acts like a wave, and outside of the box, it actually acts like a wave. So the reason why I'm going to tell you that is that if you think about if you look at how, for instance, let me give you an example. Imagine you have, so with light, imagine you have an absorbing material, a wall like this, right? And you shine a light through it. All right, so let's say our light is monochromatic. Here's my light wave, right? Sine of 2 pi frequency times t. All right, and it has some amplitude. I'll write that A. Right, when it enters the box, right? The box is absorbing, so this is an absorbing box, partially absorbing. What happens to the wave as it propagates through the box? It's not that the wave stops at it, of course, because it absorbs it. Let me make my sine wave a little taller because it emphasizes the effect. Sorry, guys. There we go. Nice big wave. Like that. Okay? And let me just draw 2 dotted lines to indicate where the amplitudes are. Like that. What happens to the wave when it enters the box? Well, the wave continues to oscillate, but the amplitude decays. And then some of the light will escape, and it'll escape kind of at the same, with whatever amplitude is left of the wave, and the same frequency. All right, and the way that this wave looks like inside of the box is proportional to a to the e to the minus x sine 2 pi vt, where x is the distance into the box. Okay, so what happens to a wave when it goes into the box? It continues to oscillate at its light frequency, but the amplitude decreases exponentially. So the light wave continues to oscillate, but the photons individually get absorbed by the material, not all of them, but some of them. And the probability of that increases exponentially as you get deeper and deeper in the box. So the amplitude of the wave decreases exponentially through the box. But if the box is appreciably transmittable or small enough, you'll get a little bit of wave out, right? It'll be attenuated considerably, much dimmer than this, right? This is a slightly transparent material, right? But you'll still get some light out on the other end. Let me emphasize that a little better. Right, you still get the same wave out, but the amplitude's much lower here on this side. Right? And it's the same idea here. Here you can think of the turning points, the potential for the harmonic oscillator to be a slightly transparent material. So some of them, so if you think about a particle moving through this box, we'll look at the motion later. Imagine the particle is moving here and it hits the turning point. The bond hits the turning point. Of course, it can bounce back and go backwards. Right? It can just do like a normal harmonic oscillator. But there's a probability that the bond or the system will slightly leak out of the box. And the amplitude of that decays as roughly e to the minus x squared, where x squared is the distance from the turning point. Right? Just like a wave penetrating a slightly leaky box, an absorbing box, is that the system, of course, can reflect and go backwards, but some of the photons will get absorbed, and the amplitude of those photons that get absorbed decreases as a function of the depth of the box, and it does so exponentially. So light decays as e to the minus x, but a harmonic oscillator decays outside as e to the minus x squared. Right? So it's actually even worse. It decays even more fast. But it's the same concept. Right? Because these systems, these harmonic oscillators, they're still waves. Right? They're still wave-like behavior. They oscillate like waves. And when you put them up against a leaky exit, partially transmittable material, they can leak through the box, and you can find them outside of the box with an exponentially decreasing probability. Just like a wave. There's a term for this. I bet you've heard this term. You never knew what it meant. But the concept of this wave becoming exponentially damped through the material and then getting released on the other side, this is called evanescence. Like the band. Seriously. I bet you Evanescence didn't know that's what it meant. But the idea that a wave gets exponentially damped through absorbing material, and then you have an output wave, which is whatever escapes. That's what's called the evanescent wave. And so this process of having a leaky box where a wave propagates through is called evanescence. All right? So a harmonic oscillator is a classic evanescent problem. So that we have a wall that works, but only somewhat. And that it allows some leaking, but the only leaking that's allowed through it is exponentially damped. Okay, so it decays very, very quickly, but there's a probability of it being outside the walls. It can leak out. Okay, so this is an evanescent system. This has huge implications for chemistry. We're not quite ready to talk about it. In fact, I'll give you an example next class of where this plays a big role. But the fact of the matter is that if you see this in all systems, I'm going to write just kind of a general comment for you to think about, and we'll come back to this again later. Just put it at the top. a take-home point, if you will. Actually, I write on the next page. Quantum mechanical systems defined in potentials that are finite in energy okay. So for instance, let me just give you some examples of some potentials that could be like this. We just saw one. Here's a potential that is like this, that's finite. The harmonic oscillator potential. Or maybe another one which we haven't studied, but you can it's not that hard to derive this, is a box that isn't infinitely high. So if I were to, hold on, sorry, there we go. A system that looks like this. Where the potential is finite. Right, I'll draw my little energy levels, for instance. Imagine we have energy levels here and here and here. And maybe we have energy levels in here that are like this. Like that. Or there are a couple of other examples, but if you have this is like a finite box. This is a harmonic oscillator, right? Any system like this, all of these systems have evanescent properties. And what does that mean? Well, that means that the wave function probability outside of the region of the boxes, right? So in this region, for instance, the shaded region, in this region, or for instance out here, in this region, these are what we call the classically forbidden regions, right? They're the parts of the space that a classical part can't reach, right? Past the turning points of a harmonic oscillator, or past the walls of a box. Regions, sorry, classically forbidden regions, not points. Right? The wave function in these regions, so I'll say forbidden x squared is not equal to 0. Quantum particles or systems, I'll change color, leak into forbidden areas, regions, with non-zero but exponentially damped probability. Okay. So imagine, I'm just going to close up 30 seconds here. Let's look at our finite box. Imagine my system is in a wave function that looks like this. Right? And there's some probability. Let me do it in terms of, I'll do it in terms of that. So let me just draw my energy through the box and out of the box. All right, so if I have a particle localized initially in this part of the box right here, right, and this energy level that's got, here's this wave function. All right. The question is there any amplitude of the wave function out here, past the walls of this box, the orange walls of this box? Well, the fact of the matter is there is, and it's exponentially damped, like I said. Right? So the wave function enters in, oscillates, but the amplitude of the oscillation exponentially decreases. And then on the other end of the box, that wave just continues on forever. Right? So the amplitude here goes as e to the minus x. So it goes to the box. psi, and this is psi. Right, and that's conserved on the other end. So if your wave function has appreciable probability to go through the box and end up on the other side, you have some amplitude on the other side, there's a probability you're going to find the particle there. Right? There's a term for this. Let me just say one more thing, that if this were a classical particle, remember it has to have enough energy to go over this box. It doesn't. So if the particle's energy is right here, classical, it's never going to go across this box, right? It's just going to bounce back and forth. It doesn't have enough energy to escape the well. But quantum mechanically, it can burrow through the box to come out the other side. There's a non-zero probability of that. There's a term for this. And we'll explore it next class with the harmonic oscillator. This idea of evanescent states, this is called tunneling. I'll write that somewhere else. All right, write it right here. All right, the process of a quantum mechanical system leaving its classical region and showing up somewhere else. Some probability of showing it somewhere else where it's not supposed to be. It's called tunnel. Right? It's a completely general phenomenon. Happens in chemistry, happens in physics, it happens in engineering. And next class we'll talk about this in terms of the harmonic oscillator, and I'll show you some examples of where tunneling plays a huge role in chemistry. Okay? All right, so we'll come back to that. All right, you guys have a lovely day. I'll see you guys on Thursday. And I'll make sure this is all uploaded for you today.